Hello, today we're looking at polynomial functions, graphs, and compositions. You can see the 5 different objectives that we'll get to in today's lesson. Starting off with evaluating a polynomial function. So if we are looking at finding f of 3, we need to take our function f of x, the function here, and we just replace all of the x's with the input that is here, in this case 3. So in doing so, we can see that f of 3 would be 4 times 3 cubed minus 3 squared plus 5. So again, just replacing the x with the input. We evaluate what we have. Of course, cubing 3 we get 27. Squaring 3 we get 9. And so then we just have to multiply the 4 by 27. So 108 minus the 9 plus the 5. So taking 9 away from 108 gives us 99. And then add the 5, we get to 104. So that's what that looks like, finding f of 3. To do the same thing for f of negative 4, we really just, again, replace the input with negative 4. And again, be careful with the negative. So again, being careful when we plug in the negative 4, f of negative 4 would look like this. Being very careful, though, with evaluating things. Specifically, people tend to struggle with squaring negatives. So again, remember, when you square a negative, you're really multiplying two negatives together, so it becomes positive. Now when we cube a negative 4, we will get negative 64 as the result, minus, and then when we square the negative 4, we get a positive 16, and add the 5. Again, we still have a little bit of evaluating to do here. So this would give us negative 256 minus 16 plus the 5. If we take the 16 away, we'd be talking negative 272 plus 5. And so that actually ends up giving us a negative 267. So that's what the f of negative 4 is. And again, we're just looking for f of negative 4. We're not trying to, again, we can't solve for f. It's a common misconception. Again, we're just evaluating the value of function f when the input is negative 4. And so what we're saying is when x is negative 4, the value of function f is negative 267. Again, it's different than trying to solve an equation for a variable. We're just evaluating for a given value of the input. Here we're going to use a polynomial model to approximate some data. Here we've got a situation, number of U.S. households estimated to see and pay at least one bill online each month during the years 2000 through 2006. It's a little bit older data. It can be modeled using the polynomial function defined by this polynomial here. They do explain here that x equals 0 corresponds to the year 2000, x equals 1 corresponds to 2001, and so on. P of x is in millions, so that's millions of households that did this, paid at least one bill online each month. They want us to use the function to approximate the number of households that paid at least one bill online each month in 2005. So, starting off with that, 2005 means that x is 5. It's not my best 5 ever. So x is 5. And so we replace the x in our function with a 5. So we're finding p of 5. That would be the point 808, not my best 8 either, times 5 squared plus 2.625 times 5 plus 0.502. So again, I would pretty well let the calculator handle doing this calculation just with the number of decimals and things involved. When I do that, again, you got to be very careful in how you enter that in, but here's what I come up with, 33.827. Now, again, they don't ask us to round. Of course, it is an approximation in the first place, but remember, the p of x is in millions of households. So this 0.827, that's actually 827,000 households. So you certainly don't want to just round this up to, say, 34 or something like that. You're actually creating quite a rounding amount there. So again, just 3.827 is the P of 5, and in terms of the original question, that's 33.827 million households in 2005 paid at least one bill online. Alright, so here we get to adding and subtracting functions. When we're doing this, here is very commonly how you'll see this written, f plus g of x. Well, really that's just adding f of x and g of x together, so very similar to just adding two polynomials. Same thing, commonly written out like this for subtraction, just do f minus g of x. Well, again, that's really just f of x minus g of x. They do mention the domain here. The domain of the new function is the intersection of the domains of f of x and g of x. Remember, intersection, that's and, so it has to be in the domain of both. Of course, when we're dealing with functions, or polynomials, I should say, the domains are going to be all real numbers, but just because they're functions does not necessarily mean that they will be polynomials. So here on this one, we're looking at adding, in the first case, f of x plus g of x, and then second case, finding the difference. As I mentioned, it's really just a matter of then here for a, doing f of x plus g of x. Well, f of x is x squared minus 3x plus 7, and then g of x is negative 3x squared minus 7x plus 7. Parentheses are really just to emphasize that here is one function, here is another. This is f of x, this is g of x, and we just combine our like terms. So combining my x squareds, I would get negative 2x squared, because I have a 1x squared minus the 3x squared. Subtracting the 3x and the 7x, I get a minus 10x, and then adding the 7's together, I get plus 14. Again, you can do a bit more as far as writing that out if it helps you to get the correct answer, but that's all we're really looking at for this one. The second part, we'll do the subtraction, f of x minus g of x. So it'll start off looking very similar, x squared minus 3x plus 7, but then subtracting negative 3x squared minus 7x plus 7. Again, one tip for doing that is change from subtracting to adding so that we can just look at adding for our operation on each of these. If I were to do that, if I'm going to change this to adding, then I change each of my signs, and so then that would end up looking like this, so that we'd be adding the 3x squared, adding the 7x, but subtracting the 7. So if I look at adding the x squared and the 3x squared, they're both positive, so I get a result of 4x squared. If I'm looking at the minus 3x and the plus 7x, be a total of plus 4x. Plus 7 minus 7 would be gone, so it's really just 4x squared plus 4x. That's what f minus g of x equals. Here we're looking at doing a similar thing, adding and subtracting functions, but big difference here is I'm doing f plus g of 2. So f plus g of 2 could also be written as f of 2 plus g of 2. So if I can figure out f of 2 and g of 2, I just have to add those together. So you can almost treat that as two separate problems. F of 2 would be 10 times 2 squared minus 2 times 2. And I can evaluate that. So f of 2 would be 10 times 4 minus 4, so 40 minus 4, and I end up with 36. So that's what my f of 2 equals. So f of 2 equals 36. I'm going to add to that g of 2. G of 2 is just 2 times 2. So g of 2 is 4. So just adding f of 2 plus g of 2, I would have 36 plus 4. I end up with 40. as my result. Looking at doing f minus g of x, so I would take, well, in here we're actually doing two things. We're finding f minus g of x and f minus g of 1. So doing the f minus g of x is just f of x minus g of x. So I would just take the 10x squared minus 2x and subtract g of x, which is just 2x from that. Not much to distribute the negative over. We just end up with 10x squared minus 4x. So that's f minus g of x. And then to find f minus g of 1, I could do that very similar to how I did a, where I just found f of 2 plus g of 2. I could also take the f minus g of x function and just replace the x with a 1. If I do that, since I already have the f minus g of x, then f minus g of 1 just becomes 10 times 1 squared minus 4 times 1. Of course, 1 squared is 1, so it would just be 10 minus 4. So f minus g of 1 is 6. You could see how you'd come up with the same thing by just doing f of 1 minus g of 1, f of 1 being 10 minus 2, which would be 8, g of x being, g of 1 being 2, 8 minus 2 giving you the 6. So either way gives you the same thing, but if you already have the f minus g of x, it's nice to just go ahead and use that. Next we're going to take a look at composition of functions. So composition is a bit of a different operation. It's not adding or subtracting, it's not multiplying or dividing. Some people do get a little confused because they see this symbol here, this open dot, if you will, and they think that that looks a lot like a multiplication dot. But again, composition is not the same as a multiplication. Really what we're doing is we are using one function as the input into another. So in this case, g of f of x can be written in this form or this one. To me, this form is a bit more apparent what is going on. That function f of x is being plugged into the function g. And again, they do mention the domain a bit here for all x in the domain of f, such that f of x is in the domain of g. Again, when you get limited domains, it can be a little bit interesting. But for us, that won't happen for a little while. So looking at our first question here, finding the composition of f of g of 4. So I would summarize like they did here, that f of g of 4, really what we're doing is we're taking g of 4 and plugging that in as the input for f. So first step is to find, in this case, g of 4. So I replace x with 4, so I get 4 plus 3. So g of 4 is 7. So if g of 4 is 7, then f of g of 4 is the same as f of 7. Well, f of 7 is pretty simple to figure out. If I'm figuring out f of 7, I just replace x with 7, which would give me 7 squared. F of 7 is 49. So if f of 7 is 49, f of 7 is the same as f of g of 4, and that's what I'm looking for is f of g of 4. Then f of g of 4 is 49. Finding some more compositions, so we're looking at f of x and g of x again. We're looking here at f of g of 2. So again, to me, I like to kind of translate that into the other type of notation. So I can see that I'm really just using g of 2 as the input into f of x. G of 2 would be 2 squared plus 5. 2 squared is 4. 4 plus 5 would be 9. So I know g of 2 is 9, so I'm really finding f of 9. F of 9 would be 4 times 9 minus 1. So it would be 36 minus 1, so that would be 35. 5. So if f of 9 is 35, then f of g of 2 is 35. They also ask here for us to find f of g of x. So we don't have a number to plug in, which means we need to just use the x for the input. So we're really finding f of g of x. So g of x is my input into f. G of x is x squared plus 5, so I'm really finding f of x squared plus 5. So when I do that, f of x squared plus 5 will be 4 times x squared plus 5 minus 1. So we get 4x squared plus 20 minus 1. So that will end up being 4x squared plus 19. So I know f of g of x. Now they ask me to go ahead and find f of g of 2 again, except now using the rule that f of g of x is 4x squared plus 19. So f of g of 2, now I plug my 2 in for the x here, so I plug it in for my 4x squared. So 4 times 2 squared plus 19. So 4 times 4 plus 19, which would be 16 plus 19, or 35. Obviously, we expect to get the same thing because it's f of g of 2 either way. So either calculating f of g of 2 directly or finding f of g of x and then finding f of g of 2 from there. So either way we get the 35. Next we'll take a look at some different graphing processes. So we'll take a look at a linear function, a quadratic function, and a cubic function. So a function like f of x equals 2x, we want to just take the simple approach by creating a table of ordered pairs in order to graph this. And then we'll try to build an understanding of the domain and range just by looking at the graph. If I'm going to make a table of values, typically I'll pick values around 0 for the x, so they go -2, -1, 0, 1, and 2. And so really all we do then is find f of -2, find f of -1, find f of 0. And again, here's our function. So f of x equals 2x. So if x is -2, then f of x is -4. And we can see the different values that we get here. Those translate to these points on our graph. We can connect those with a line. The domain is all the possible x values for that function. The range is all the possible y values for that function. This line has arrows on both ends, meaning that it goes forever down and to the left, forever up and to the right. There are no holes in this graph anywhere. So the domain and range both are -infinity to infinity. And that's true for any linear function like the f of x equals 2x. Next we'll take a look at the squaring function. In this case, f of x equals the opposite of x squared. Again, I would pick values around 0, -2, -1, 0, 1, and 2. And if you need to do more, maybe the graph is shifted left or right considerably, then you can always pick more points once you have a basic idea of what the graph looks like. In this case, plugging in the different values for x, again, very careful about how you evaluate those, especially with squaring an x and then taking the opposite of it. So when we square -2, we get a +4, but then the negative means we get a -4, and so on for the -1, 0, -1, and -4. Notice the symmetry there, -4, -1, 0 in the middle. And we can see that symmetry in our parabola here. It's upside down because of the negative on the x squared. But we can see, again, those ordered pair values on our graph. Again, the domain is all possible x values. Again, this arrows on both ends of this go down and out. So down and to the left, down and to the right. So left and right are completely covered. So the domain is -infinity to infinity. The range, however, notice neither arrow comes up. Both arrows continue down. So the maximum for this function for y is 0. So in our interval notation, you can see the range is -infinity up to 0. 0 being the maximum for the range. There are no points on this parabola that are above 0. So the range is only negative infinity up to 0. And next we'll take a look at the cubing function. So we've got an f of x equals x cubed minus 2. Again, if you just pick values around 0, should serve you pretty well. If the graph is shifted considerably left or right, then you can continue to come up with more points. Again, very careful how you plug the values into the cubing. Just cube it, take 2 away, and we get these points for our table. So negative 2 cubed would be negative 8. Take 2 away, we get negative 10. And so on for the other values in that table. When we look at those 5 points, these are really the 5 that we would want to have for any cubic function. There's going to be 3 points kind of right around the curve in the middle of this graph, and then if we get the next one on either end of there, it really helps graph it, because if you look at these 3, they actually, if you didn't have any other points, you might think that that was a line. Of course it's not. So it actually goes like this. So this is what our graph looks like. Again, arrow on the left goes down and left, arrow on the right goes up and right. So it's got left and right completely covered, so domain is all real numbers. It has up and down completely covered, so the range is also all real numbers. So domain and range both negative infinity to infinity. Again, there are no holes in this graph. There are no values of x that make it so that we don't get a real value output for this function. And there are no values of y that we cannot come up with by having some value in there for x. So hopefully you found this helpful for learning about composition of functions and how to graph a few basic functions. Thanks for watching.